Today we are talking about Chapter 10, Section 1, Systems of Linear Equations and Two Variables. Okay. I think this is a pretty simple concept. I do feel like I say that a lot though, so forgive me. All right, from the top. A system of equations is a set of equations that involve the same variables. A system of linear equations is a system of equations in which each equation is linear. A solution of the system is an assignment of values for the variables that make each equation in the system true. To solve a system means to find all solutions of the system. Okay, so a linear equation in two variables is an equation of the form ax plus by is equal to c. So here's an example of a system of linear equations. So basically, a system of linear equations is literally what it is, right? It is a system of linear equations, right? So we see a bunch of linear equations, we take the system of it. Okay, so it's kind of like we talked about with piecewise functions, right? Piecewise functions is a function, but it's a function with multiple functions. It's kind of like, your teacher's giving you a quiz, and you ask how many questions are on the quiz, and they say 5, right? But each one of those has like 3 parts, so it's really like 15 questions, right? That's kind of like this. It's cheating. This is instead of just one equation, it's 2 or 3 or 4. I don't know. Actually, we're only doing 2, I think, today. Yeah, matter of fact, that's what it says, Sherman. So yeah, we're only doing 2 today. But anyways, enough blabbering. Let's move on. Okay, so probably should have. Can I fit that here? No. Okay, so let me fix something. I don't want that, so we're going to go to there we go. Okay, so we see our example of a linear equation, a system of linear equations. Okay, and it says we can check that x equals 3 and y equals 1 is a solution, and we can check that by plugging them in. And then it says the solution can also be written as ordered pair of 3, 1, because 3 is taking the x part and 1 is taking the y part, which we see here. We can also see that 3, 1 is where they intersect on the graph. All right. Again, the blue line is x plus 4y is equal to 7, and the red line is 2x minus y is equal to 5, and where they intersect 3, 1 is the solution of those equations. And of course, we'll delve deeper into that here in a moment. Alrighty, so the substitution method. I think we can just take out all this. No, let's do this, actually. New page. Okay, so the substitution method, again, it is, we can follow along with that. However, I like to do things without following along with that. You know me. At least you should by now. Instead, we're going to do it with my words. All right, so my words. Find all solutions of the system. So this is going to be, so we have substitution, cancellation, and graph. Okay, so the substitution method is one of 3 methods we use to solve systems of linear equations. Now, between substitution and elimination, you might ask yourself, okay, so which one should I use? Okay, and of course we'll get to that later. Hopefully I can remember that question, right? Which one do we use? Well, the one we use is the simplest method. And you're going to know when to use the substitution method, mainly because here we are looking at our variables. Okay, if one of those four variables, there's two variables, but we one of these four here, right, has a coefficient of 1, then that should tell you which method you should use. And in this particular case, it would be a substitution method. All right, so before, again, I blabber too much, let's see why. All right, so a substitution method is exactly what it sounds like. We're going to substitute. So I said we're going to use the one where we have a coefficient of 1, right? So what we're going to do is we're going to take this entire equation, and what we're going to do is we're going to solve for y. Okay, if we solve for y, that's pretty easy. It's going to be y is equal to 2x minus 1. I'm sorry, negative 2x. Let's just do 1 minus 2x. 1 minus 2x. Okay, so that's my value of y. So what I'm going to do is I'm going to substitute this y value in for that y value in equation 2. Okay, so my equation will become 3x plus 4, and then we said my y value is 1 minus 2x. That's equal to 14. Okay, now let's solve for x. So we've got 3x plus, looks like 4 minus 8x. So 4 minus 8x is equal to 14. Alright, so let's keep the x's on the left and put the constants on the right. So in order to do that, we're going to have negative 5 and what, 10? Yeah, negative 5x is equal to minus 4, yeah, 10. And then if we divide both sides by negative 5, we have x is equal to a negative 2. Okay, so this tells me what my x value is. So what I'm going to do here now is I'm going to take this x value and I'm going to substitute it back into the first equation. Okay, now you have to put it into the first equation because if you put it into the second equation, you're just going to get a true statement. Okay, you're going to get something like 7 is equal to 7. That, of course, that's true, right? So what we're going to have to do is we have to plug it into the first equation. And so when we do that, we end up with, let's see, how can I do this? I guess we'll keep this, let's put this in yellow actually, because I like to reserve white for something different. So y was equal to 1 minus 2x. 1 minus 2x. Okay, so okay, so we're going to plug in negative 2 back into my first equation. So we're going to say y is equal to 1 minus 2, and then we said x was equal to a negative 2. And so if we solve here, we've got y is equal to, well, a negative 2 times a negative 2 is a positive 4. Positive 4 and a 1 is a 5. Okay. So my solution here will be the point negative 2, 5. And again, the negative 2 is the corresponding x value, and the 5 is the corresponding y value. And of course, if we plug these back in, and let's just do it, I guess. If we plug in negative 2 and 5 into these equations, okay, so 2 times negative 2 is negative 4. Negative 4 plus a 5 is 1. 1 is equal to 1. Good. We plug it into this one. Negative 2 times 3 is negative 6. 4 times 5 is 20. Negative 6 plus 20 is positive 14, so that's true. Okay, so we do indeed see that negative 2, 5 is a solution to this system of linear equations. Okay, this is the substitution method. And again, you're going to know when to use the substitution method. Again, you could use either, well, actually all three of the ones that we're about to use. Okay, but when we do things algebraically, we like the path of least resistance, don't we? So the path of least resistance here would be looking at the coefficients of my variables, and if I have a 1 in front of one of them, then I'm going to proceed with the substitution method. At least that's my own personal rule. We'll leave the graphing alone for now. All right, next up would be the elimination method, and again, here we go. We've got a nice little 1, 2, 3 step that we're not going to even talk about. Again, I put on the notes though in case you're there, but I like to do things, list things my way. So, well, actually, this definitely violates the thing I said about you'll know which one to use, right? Because honestly, if I was to look at this particular problem, I would go straight ahead with, well, that's not true actually. Okay, so the elimination method, what you're going to do is you're going to essentially look at this as an equation on top of another, right? Y'all remember doing like long division whenever we would have a polynomial over another polynomial and we subtracted, right? And that's essentially what we're doing here, right? So, here we're just going to be adding these two together. So 14 over 2, well, that's 14 plus 2, that's 16. A positive 2y and a negative 2y, well, that's going to be 0y. I'm not even going to write, actually, I will write 0y. 0y. And then 3x and an x, that is 4x. Okay, so hopefully that makes sense. Actually, let's go ahead and write this out. I really want to drive this point home. Okay, so basically, again, I'm just adding I'm just adding these two together. Okay, so again, let's just start from the left instead of the right this time, right? So 3x and 4x, so that's going to be, 3x and x, that's going to be 4x. And then a positive 2y and a negative 2y, well, those are just going to cancel. That's going to be equal to a 14 and a 2, which is 16. So we have x is equal to 4. Okay, and that's actually a lot easier. So sorry about what I did earlier. That's confusing. Good job, Sherman. Way to go. So anyways, once we have this value, x equals 4. Okay, now remember, with the substitution, it definitely mattered. 100% it mattered where we plugged in this value here. We had to plug it in to my first equation, which was plugged into my second equation. Okay, and it mattered. I haven't had my coffee this morning, sorry. This, it doesn't matter, right? Because we're not there's no we're not substituting into an original equation per se, right? So we have x equals to 4 once we did the elimination method. Okay, so x equals 4. It doesn't matter which one I plug it into now. So I'm going to plug it into what I think is probably the easiest. And in my opinion, I mean, I would much rather plug it into this one than this one, right? But it doesn't really matter because you're going to get the same solution either way. All right, so let's plug it into the second equation. So we have x, actually, let's put that as over here. We're going to say 4, and then we'll just write this minus 2y is equal to 2, right? And then let's do the arithmetic here. So if we subtracted 4 from both sides, we've got a negative 2y is equal to negative 2, so we have y is equal to 1. Okay, so this means that the solution set, okay, the x value is a 4, and the y value is a 1. And that's it. Right? And of course, I don't want to actually write it. I will write it, but I'm going to erase it after. Okay, after the fact. Okay, so we could have plugged it in here, right? 3 times 4, and then plus 2y is equal to 14. Okay, so we're going to do some mental math, follow along. 3 times 4 is 12. I subtract 12 from both sides. I get 2y is equal to 2. And then if I divide both sides by, did I say 1? It's supposed to be negative 2 over here. Sorry. Oh, yeah, I did do that. And then 12. I'm sorry. I messed, again, coffee, right? I was looking at my second problem. So let's try this again. 3 times 4 is 12. I subtract 12 from both sides. I get 2y is equal to 2. And then there I get y is equal to 1, which is the exact same thing I got when I plugged into the second equation. Whew. Right, so I can't blame coffee, guys. I'm sorry. That's done with me. That is how we do the elimination method. So we did the substitution. We did the elimination. Now the last one is, depending on how good you are with the calculator, by far the easiest. But I will say this, it is the one we're going to use the least because I hate calculators. You're lucky you're not in a classroom with me because I don't allow calculators. Calculatus. All right, here we go. So new page. Actually, this is definitely one that I can just snip all the way through because I am not going to bring up a calculator. So we saw at the very beginning of the lecture that my system of linear equations, the solution, if I graphed it, would be where they intersect. And that's true. Okay, so if I were to graph both of these equations, okay, where they intersect, right here, I guess the solution here would be 0.3 and 1.3. Okay, and I mean another instance of hand waving, right? But that is just the solution. It's where they intersect. And to be honest with you, I haven't done intersect in a long on my calculator in a long time, so I couldn't even tell you how to get to that. I mean, I'm sure a quick Google search and like maybe 2 minutes of research can figure that out. But that's that. And of course, we could, if we wanted to, we could use either the substitution method or the elimination method for this, if we didn't want to use a calculator. But the decimals really make it kind of right? All right, so next we will have the number of solutions. Wow, today's a pretty short lecture. I'll have to make it smaller. There we go. Okay. So, number of solutions of a linear system in two variables. The graph of a linear system in two variables is a pair of lines. So to solve the system graphically, we must find the intersection points. Two lines may intersect at a single point. They may be parallel or they may coincide. Okay. So far what we've seen is this: two separate lines that meet at one point. Of course, that makes sense, right? If a line that goes on and on and on and on and on and on forever, right, is going to intersect with another line that goes on and on and on and on and on forever if they are not parallel or the exact same line. Okay, so your three possible outcomes will be: you have one solution where they intersect. If the two lines are parallel, obviously they will never intersect. Makes sense. And this is actually pretty cool. They actually made that line purple, right? So if we stack the red line on top of the blue line, they will essentially be the exact same line, and therefore there will be infinite many solutions. Excuse me, infinite many solutions, right? Because a solution for one equation will be the exact same solution for the other equation. So those are your three possible outcomes: one solution, no solution, or infinitely many. And down here, it reads, and for those of you in the Zoom call, I'm pretty sure you see my toolbar and stuff, but obviously on YouTube, you don't see the toolbar there. But anyways, a system that has no solution is said to be inconsistent. A system with infinitely many solutions is called dependent. There you go. There's some words for you. I know you're just dying for words, so there we have it. Okay, so this will be pretty easy. This is going to be a linear system with one solution, which we have done before. We're just basically doing it again. Okay, so here's the thing. We could, let's see how the book was going to do. Okay, so the book looks like they're doing through elimination, and that's fine. Okay, what they're doing here is, oh, well, you can't see. Well, I mean, you can see, but down here, it looks like we're doing the elimination method by multiplying the top equation by 2, and then we're eliminating the y. Okay, there's nothing wrong with that. And honestly, I'm going to do this both ways. Okay, because I said earlier, in my opinion, you know, if you see a variable with a leading coefficient of 1, go ahead and do the substitution method. But I'm okay with the textbook using the elimination method there, mainly because the elimination method is a method that you need to become most familiar with. All right, it's the one that moving forward, especially when you get to matrices and such, you are going to be using the elimination method. Okay, so we're going to do both methods for this one. Yeah, we'll do both methods for this one. Okay, so obviously, if I were to rearrange that top equation, I would get negative y is equal to negative 3x. So therefore, y would be equal to a positive 3x. Okay, and so I'm going to plug that into my second equation. So 5x plus 2 times 3x is equal to 22. So proceeding here, I got 5x, and then I've got plus 6x is equal to 22. So 5x and 6x is 11x, 11x and 22. That's going to be x is equal to 2. Okay. So I've got x equal to 2. I'm going to plug that back into my first equation there. So it's going to be y is equal to 3 times 2. And that's pretty easy, right? So y is equal to 6. So my solution set here will be, let's put it in green, will be 2, 6. Okay. This is the substitution method. All right. Now I'm gonna do the exact same problem with it, and I'm gonna do the elimination method, because it didn't really when we first began, we didn't really do the whole multiplying a line by, right? Because when we did the elimination method, excuse me, it just so happened that we have the two variables there. They already have the same they already have the same leading coefficient. It's just one's a positive, one's a negative. Okay, so if I wanted to do the elimination method here, which I'm going to obviously, let's do this. Let's rewrite it. Okay, so if I want to use the elimination method, I'm going to look at my variables. I'm going to look at 3 and a 5 and a y and a 2, or a 1 and a 2. Okay, so it's very easy to see that I can eliminate the y's pretty easy, right? Because I've already got a minus sign and a plus sign in front, right? So one component's gonna be, or one of them's gonna be negative, one's gonna be positive. So what I'm gonna do is I'm gonna multiply this entire first problem here. I'm gonna multiply the entire top one here, sorry, by 2. Okay, that makes sense, right? So I'm just gonna take this and distribute 2 through. Now I'm not changing the value of, I'm not changing what this graph looks like. Right? If I were to graph 3x minus y is equal to 0 and 6x minus 2y is equal to 0, it's going to be the exact same line. So I'm not changing the line whatsoever. All I'm doing is just getting a multiple of that line. Okay. So we can now rewrite this. Let's go ahead and rewrite this as, again, multiplying it by 2 would be 6x minus 2y is equal to 2 times 0 is just simply 0, right? So if I were to do the elimination method, well, 6x and 5x, so that's 11x. The two y's cancel. That's going to be equal to 22. And of course, we have the same thing. X is equal to 2. Okay. And then I said, it doesn't matter which one you plug it into, as long as you plug it in, right? So let's just go ahead and plug it into the top one. So the top one would be 3 times 2. And then it's going to be minus y is equal to 0. 3 times 2 is 6. 6 minus y is equal to 0. Negative y is equal to negative 6, or y is equal to 6. And of course, this is the exact same thing because we saw on the previous page. We have the point 26 as the solution. Okay. So it doesn't matter which one you use, but again, elimination, that would be the one that I would suggest you do most, like 90% of the time, unless something is just blatantly obvious that you should do something else. Again, mainly because you're going to be using the elimination method a lot more in the future. Of course, I do it graphically as well. Okay, so that is a system with one solution. Now let's look at a linear system with no solutions. Okay, and actually, do I even have room? Let's try this. I'm going to go ahead and put the graph of it there. Put it off to the side, maybe. There we go. Okay, and of course, so we did do it through substitution, elimination, and then graphically. So that was a system of linear equations with one solution, which would be, I guess, our fourth example of it, right? Now we're going to do one with no solution, right? And a linear system with no solution, as we saw before, would just basically be two parallel lines. Now, the thing is, looking at this, you might not be able to tell if they're parallel lines. Okay, so that's why we have to do this system of linear equations. So, really quickly, this is definitely going to be an elimination, and it doesn't look like it matters what I eliminate, right? But because I want to make things a little bit easier, what I'm going to do is I'm going to eliminate the y's. Okay, so I'm going to eliminate the y's. So what is the smallest number that both of those will go into? Right now, I say smallest because obviously we don't. I mean they both will go into 60, right? But I don't feel like multiplying the top by 30 and the bottom by 20. So instead, what I'm going to do is I'm going to look for the smallest number. So the smallest number obviously would be 6. All right, so I need to multiply. It looks like I need to multiply this top one if I want to turn this negative 2y into a negative 6y, and multiply it by a 3. And then the bottom one, if I want to turn that 3y into a 6y, I need to multiply it by 2. Okay, so again, a top by 3. Let's go ahead and write that. Multiply by 3. I'll multiply this one by 2. Okay. So if I write this out, so I multiply the top one by excuse me, by 3, I'm going to get 24x minus 6y is equal to 15. And then the second one would be a negative 24x plus 6y. That's equal to 14. I say ooh because hopefully you see it as well. All right, looks like this cancels and this cancels, so I got a 0 over here, and it's equal to 29. Okay, we know that 0 does indeed not equal to 29, right? So that's a false statement. So this is a linear system with no solution. Okay, these two lines are parallel. Let's see. Oh yeah, probably have the graph. Just gonna try and yeah, there we go. I don't suppose I need to do put the figure in there. There we go. So we see if we graph both of these equations that they are indeed parallel lines, right? If we solve for y, they would be the exact same equation. So these are parallel lines, a linear system with no solution. This is what it looks like algebraically. Very incorrect, right? No, let's not put the x. Let's not put the x over it. Alrighty, and then the last one, right? So I told you today was a pretty simple day. The last one we have is a linear system with infinitely many. Okay, so these two, if it's infinitely many, then they're going to end up being the exact same line, right? So let's begin. Looks like we can the 3 and the 4. Let's go ahead and cancel the 3 and the 4. So, but unlike the previous few examples, they do not have differing signs. So I'm going to have to make different. I'm going to have to force a different sign, right? So 3 and 4, the smallest number that they both go into would be 12. So what I'm going to do is I'm going to multiply the top equation by negative 4. Let's just multiply the top one by a positive 4 and the bottom by a negative 3. Okay, and doing so, I end up with 12x, and then 4 times 6, so that's a negative 24y. That's going to be equal to, sorry about that, 48. And then the next one's going to be a negative 12x. Okay, good, perfect, that's what I'm wanting. And then 8 times, so it's going to be plus 24y. Okay, it's going to be equal to 16, so it's going to be equal to negative 48. Okay, and then I got my equal sign here, and then, well, look at this. I've got 0 here. Well, this zero's out, this zero's out, and this zero's out. Okay, so they all zero out, right? And we have a true statement now. So since we have a true statement, this must mean that these two lines are the exact same. Okay, now let's look at the difference here. If we have no solution, then we're going to have us a false statement. 0 is equal to 29, 7 is equal to 4, something like that. If we have a true statement, 0 is equal to 0, 7 is equal to 7, something like that, then we have a linear system with infinitely many solutions. Okay? And of course, if we graphed it, we would see that they do indeed, or they are indeed rather, the exact same solution. And really quickly, let's try this instead. All right, this is the previous example. Let's put that down there. Can I do that same? Can I do the same right here? So what I want to do real quick is I'm going to solve for y. Okay, so if I solve for y, this is going to be negative 2y is equal to negative 8x plus 5, and divide both sides by negative 2. I've got y is equal to 4x minus 5 halves. And then this equation, if I solve for y, I'd get 3y is equal to 12x plus 7. And I've got y is equal to 4x plus 7/3. Okay, so looking here, and let's actually box these, I guess. Looking at this, we see that these two lines, these two linear equations, have the exact same slope of 4. Okay, and since they have the exact same slope, that is why they they're parallel, and therefore they never intersect with one another, and therefore there's no solution. Okay, so that is just another way to look at this, and that's why this false statement creates the no solution. Let's look at this one. Let's solve both of these for y as well. So we got negative 6y is equal to a negative 3x plus 12. So we divide both sides by a negative 6. So we've got y is equal to a positive 1/2 x minus 2. And then this last one, we're going to solve for y again. So we got negative 8y is equal to 4x. I'm sorry, negative 4x. Negative 4x plus 16. Divide both sides by negative 8. We've got y is equal to 1/2 x and then minus 2, which here we see that they are the exact same equation, right? Now, obviously, if they're the exact same equation, then of course they're going to overlap one another. So that's another way to think about it intuitively, right? And of course, if we have that true statement, they will be the exact same equation. Anyways, that concludes today's lecture.